Lecture 11a, local properties of covariant derivative. You see, as I said, I emphasized on last lecture, our goal here is to obtain tools, develop tools that such that will be applied to the curvature. See, that's important for you to understand why I'm deriving these properties. Now, property 1, linearity in the vector field. As I pointed out in the lecture 10, see, this is a linear vector field here. This is a B being differentiated, you see? So, a statement, what I want to show, dx ay plus bz is a dxy plus b dxz. A and b belongs to a real number. Okay, the derivation in coordinates, I can express the vector y is yj partial of xj, you see, and zj partial of xj. Doesn't matter, could be zk partial dxk or zi partial dxi. Since j this case is dummy, see? So this dx ay, that's what I expand. So I substitute, you see, this is a partial yk xi plus b zk partial xy. You see, this I call here, for instance, a w, okay? I can expand here as the sum of ay plus bz. So this here leads to a here and a over here and b and b. You see, I separated, okay? Now, this is a xi. You see, remember that x here is a vector, okay? Xi partial the xy. Now I can group, you see, this term here with this term over here. So this a xi partial yk respect to xi plus Christoffel symbol yj. Now I repeat here, then I can group b here and b over there. So bxi, just the same, I just copy from here, dxi. So then you can see here in this parenthesis that this case is the vector capital Y, and here is the vector capital Z. I just set here dx ay plus bz is a dx y plus b dx z. So this is a linear, you see, in this case of the vector field. Now the property number 2 is linearity over functions, okay? Or in this case, in the direction of vector field. You see? Now the statement dz fx plus gy, you see, this is I want to show that f dxz plus g dyz. Then I call this sum over here, fx plus gy, I call it as capital W, okay, and apply the definition over here. So this is wi, you see partial of xi over here, and this is the vector. This case is the covariant of the vector of z. You see, that's quite easy to show this. This is a covector, okay? This case, okay, the covariant derivative. I'm sorry, not covector. Covariant derivative of z. Then wi, you see these two terms over here. Thus, I can substitute. You see wi here, you see fxi plus gyi, then they multiplies this covariant derivative of z, okay? Don't forget, this is partial xi. Now, then I can, in this case again, I can group, okay? I can group here, you see, this fxi, zk, partial, Christoffel symbol, this k, gamma kij, zj, the partial xi, plus, now, I can group this term over here, so gyi, this here is the covariant derivative of the vector z, okay? And also, don't forget the basis partial xi. Now I can substitute over here, okay? What is this? This is covariant derivative of z, which is written over here. So f dx xi partial with respect to xi, then I can write easily that this is dx of z plus g dy of z, covariant derivative. Covariant derivative of z, covariant derivative in this case was and the same z, this is the x and this is y, see, according to the definition. So the next properties I will derive in the other 11b, okay, the other lecture 11b. So this is quite clear, okay? Again, you get a paper, pick a paper and write on, okay, on this and repeat. Copy here and repeat and check, you see, this derivation.